Hello folks, this is CIS 2353 and this is your facilitator and instructor, John Baugh. We are on week 12. It's been a couple weeks since you've had a video. If you're watching this in the 2015 year, so we've got the binary search trees that were very similar to binary trees, and then I had you do sorting on your own, and also your assignment here was assigned last week. This week we're covering tree maps and tree sets, so that's chapter 12. Next week is the Thanksgiving recess, so there will be no classes and no uploads, so that's a free week for you to work on practicing things, and etc. So your capstone project will be assigned the week following Thanksgiving recess. So let's get started. This chapter talks about tree maps and tree sets, which are data structures which are used in Java and are provided by the Java Collections framework. They're different kinds of balanced binary trees, specifically are based on a balanced binary tree called a red-black tree. It's a little bit of a looser implementation of an AVL tree, which you were probably looking into in binary search trees. The red-black tree we will discuss here shortly. And then the Java Collections framework has the tree map and tree set, which are based on the red-black trees. You've got the tree map, which has two objects, or two parts in the object. It's got a key part by which an element's compared to other elements, and then it has a value part, which is whatever the rest of the element is. No two elements in a tree map object can have the same key, so that's a rule of the tree map. And then the tree set, which we'll talk about in just a little bit also, that object is a tree map also, but all the elements have the same value part, so they have different keys but the same value. And then there are applications provided in the book we won't go into in detail, but you can practice them. There's a thesaurus for the tree map, and then there's a spell checker used for the tree tree set. So what is a red-black tree? We have to understand some of the theory behind it to know what the underlying data structure looks like. So our red-black tree is a balanced binary search tree. So it has a balancing to make sure that the different sides are well balanced. A red-black tree is a binary search tree that is empty, that's one possibility, or in which the root element is colored black, every other element is colored red or black, and then there are two rules that must be followed. The red rule, for an element colored red, it cannot have any red children, so that's one of the rules. Another rule is called the path rule. This one says that the number of black elements is the same in any path from the root element to any element with no children or with one child. So, this may seem a little bit peculiar, and you might not know, what's up with the coloring scheme, but basically this prevents us from having heavily unbalanced trees. So, again, the root will be black, that's for sure, and then note that any red element can't have any red children, and that the number of black elements on any path, that means from one node to another, they're talking specifically from the root, and then if we look at that path from the root to any element with either no children or with one child. Okay, so if it has no children, then that's a leaf node, or a node with one child. So that means that the black elements for all the paths in the tree have to have the same number of black elements. So the following are red-black trees. This is a red-black tree. If you'll notice, if we want to look at the definition again, the red elements cannot have any red children. Let's see if this tree adheres to that. Well, there's a red element. It has two black children, so that is good. And then this one's a leaf, so it doesn't have any children, so that one's good. So we have this one satisfying the red rule. The path rule says that the number of black elements is the same in any path from the root to any element with no children or one child. So let's look first for all the children with no children or one child, or nodes with one child or none. So this is a leaf, that's a leaf, and that's a leaf. So these three have to be considered. And also this one, because this one is a node with one child. It does not have two. This one will not be considered, and neither will the root itself. So let's look at the root. We've got the root, and then if we go to here, we see that there are 2 black nodes in this path. Okay, now what about from the path to this leaf? Well, 60 to 80 to 90, there are still 2 black nodes in that path. What about from 60 to 20? 1, that's not a black node, and then 20, so there are 2 black nodes. Same thing with 50. 60 to 30 to 50, there's 2 black nodes. So this actually adheres to the, satisfies the path rule as well. So it's very, very useful to understand this. This keeps there from being a balancing problem. Let's look at this one. So for example, you've got 60 to 90. 60 to 90 and 60 to 80 both have 2 black. From 60 to 20, 2 black. From 60 to 50 and 40, we got 2 black and from 60 to 50, and then since 40 is red, that's 2 black again. So this one's a red-black tree. What about this one? Notice it's got the same numbers in it, but look how they colored it. Instead of having 90 and 80, they switched the 90 and 80, so this one has red. So let's look here. We've got 60 to 90 is 2 black, 60 to 20 is 2 black, 60 to 50 is 2 black, 60 to 40 is 2 black. So far so good. What about 60 to 80, since it only has 1 child? 60 to 80 only has, 1 black node, so that means this is not a red-black tree. So the path from 60 to 80 has only 1 black element. Okay, then they give some more examples. Whenever it's violated, they can do a rotation. This tree violates the red rule, so red cannot have red children, so that would be a problem. So you can always do rotations. They explain the technique for doing rotations. But the rotation basically moves it back to a position where it is a red-black tree. So that is one way to keep the tree balanced. Okay. Oh, the height of any red-black tree is logarithmic in n. So we would say it's if you're looking for complexity, it'd be O of n, but we'd say it's log of n. Log base 2 of n is the height of any red-black tree. It's a binary tree, so we say log base 2. The height of the tree, given n nodes, is logarithmic in n. So that does give, they give an example and some explanation in that example in the appendix 2. So the next thing they ask is, what is the minimum height? Okay, so minimum height. The height and the minimum height, they got, suppose a red-black tree is complete with all black elements except for red leaves at the lowest level. That means then the height of the tree is approximately in or log of n. Okay, the maximum height is 2 log n. Okay, suppose a red-black tree has all black elements except that one path from the root to a leaf has as many red elements as possible. Then the length of that path and the height of the tree will be maximal. The length of that path is approximately twice the minimal height, so the maximum height of a red-black tree will be roughly 2 log n. Now, one thing to note about this is that the maximum height of an AVL tree is smaller. It's about 1.4, I think. Let me see if they have it in here real quick. Pretty sure they made some sort of mention of it, but it's less than 2 log n. So we would actually say that a red-black tree is by necessity, or I'm sorry, an AVL tree is a red-black tree, but not vice versa. So an AVL tree is a little more strict than a red-black tree. The AVL tree, the Adelson-Velsky-Landis tree that they talked about in the last chapter, has a smaller maximum height. Okay, the next thing we want to do is look at maps. Okay, so a map, since these are the data structures we're actually interested in, a map is a collection in which each element has 2 parts, a unique key part, and a value part. For example, we can create a map of students in which each key is the student ID and each value is the student's GPA. Just as with linked list and binary search tree, each element is stored in an entry object. The public map.entry interface has getKey and getValue methods. So the tree map in the JCF stores a map in a red-black tree ordered by keys. In the class heading, the type parameters are keyed as, or described as, k and v, which stand for key and value. So we would say a public class tree map, key and value, kv. It implements sorted map and extends abstract map. Here's your example here. So map is an interface, keep that in mind. Here are the method specifications for several methods in the TreeMap class. The TreeMap class does not implement the collection interface because many of the methods are key value oriented in TreeMap, and they are not so in the collection interface, even though we do consider this map a collection. So then they go through and they tell you some of the details. The worst time is O of n for the determining if something contains a value. Worst time is log of n for removing. Then they go through a couple other things. We can view a tree map object as a set of entries, as a set of keys, or as a collection of values, and then iterate accordingly. Okay, so they're going through an example here. They go through the example in the book a little bit more in detail, so I'll let you read through that or read through the slide. These are the fields of the tree map class. So you've got the entry, size, mod count, and then a comparator to let it be compared, even though it does not implement comparable. It allows you to describe a comparator, define a comparator. Okay. Okay, another example. That's why there's so many slides in here. There's a humongoid example here. I'm going to try to get to the next definition, or the next topic here. So this is the application they do with the tree maps. If you implement this, it will give you a much fuller understanding of the tree map. So they talk about the thesaurus and how to implement it, and then how to open files with this as well. So, okay, let me see here. That's tree map. Tree set. Okay, there's the next topic we've been waiting for. So the tree set's a little bit different. Tree set is an ordered collection in which duplicate elements are not allowed. Tree set class has all of the methods in the collection interface, add, remove, size, contains, etc., plus toString inherited from abstract collection and several constructors. These are some examples of things that it implements and extends. It extends the abstract set class, and it also implements sorted set, clonable, and serializable. Okay. Some of the constructors, it can take a collection as a copy constructor. It can take a comparator, and also be a no arg constructor as well. Here's a pair of declarations and a few messages. The by length class was defined earlier in a previous slide. So they show you how to use the tree set. So even without knowing the details, too many details, they're showing you how to use it. So it's interesting. Tree set is implemented with a tree map in which all of the values are the same. So the keys are different, but the values are the same. Okay, tree set class has the same methods as the binary search tree class, but is faster, at least in the worst case. For add, remove, and contains, worst time is logarithmic in n versus linear as the worst case in binary search tree class. Because with binary search tree, the worst case scenario in binary search tree, since it is not self-balancing, it could degrade into a linear structure, and that would be a problem. That would basically make it a line, and then it would take, at worst case, n instead of log of n. All right, so I would say go through the examples in the book and just implement them, and then use some of the examples they give for using it, and see if you can come up with your own example. They have the run method that they've defined in here. For example, for the tree map on page 509 of the current Collins book. So go through that example and make sure that you're understanding what the tree map and the tree set are, and also make sure you understand the. If I were to ask you something like, is such and such a red-black tree, be able to tell me whether it is a red-black tree or not. The rotations, at least be familiar with them, but you don't have to. You won't have to replicate it. All right, so that's a pretty brief. I just wanted to make sure you understood it fairly well. Sorting is important, but knowing that all these different structures are available and all these variations on binary trees are available is very important. So if you have any questions, please feel free to email me at jpbaugh@oaklandcc.edu, and have a good week.